questions about the green sheet, acid-base chemistry? Okay, let's look at the you
Dr. Stevens,
hey,
could I have that green sheet? Thanks.
there we go. Okay, guys. As I mentioned last time, this is sort of an outline. I also want you, as we go along, to fill in reagents on each line. Okay, use this to organize. We will refer to some of it. We'll be working back and forth between these two sets. One is sort of typed, and one is got some handwritten stuff in it. Chemistry of acid derivatives. Everybody's got a textbook. This is the Klein textbook. Use your table of contents if you got a different textbook. Synthesis of carboxylic acids. Okay, these are called acid derivatives. They're derivatives of carboxylic acid. One thing we need to point out, I didn't include it in the nomenclature video. All carboxylic acid derivatives are at the same oxidation state as a carboxylic acid. If you look at a carboxylic acid, here, the carbon has how many bonds to a more electronegative atom? 3. If you look at an acid derivative, well, I mean, how many does this have? 3. You're at the same oxidation state. Okay? What about a nitrile? Now this is the carbon of the functional group. How many bonds to a more electronegative atom?
3.
3. See, they all have 3. They're all at the same oxidation state. On the other hand, if we look at a ketone or an aldehyde, how many does that have to a more electronegative atom?
2.
Only 2. That's a different oxidation state. Aldehydes and ketones are at a different oxidation state. They're different. Okay? They're not considered acid derivatives. You can convert between all these acid derivatives without doing redox. Okay, let's start by synthesis of carboxylic acids. And let's see what's on the other sheet. Some of these will be reviewed. Here's how you make carboxylic acid, or at least the ways we will cover in this course. Benzylic oxidation. You take this compound, treat it with KMnO4 or sodium dichromate, etc. You can get benzoic acid. Anything new there?
Nope.
No. But see, this is a way to make a carboxylic acid. Well, we saw that during test 2 material, right? Benzylic oxidation. We've actually seen other ways to make carboxylic acid. We can oxidize a primary alcohol. You take this, you treat it with one of the big 3, you get the carboxylic acid. Same number of carbons. This carbon ends up becoming carbonyl. What's the intermediate here? First oxidize to the aldehyde. And then you get the carboxylic acid. It does require water. That's where the other oxygen comes from. But we talked about that during test 1. Okay? Oxidation of aldehydes. You have an aldehyde, you can oxidize it to the carboxylic acid. Of course, that's what we just did right there. A unique reagent that only oxidizes aldehydes is what? Collins reagent. Okay? It's usually that silver ion. But how does that going to look in terms of reagents? It may not just be sort of a neon silver ion. Okay? Like, what's the ammonium hydroxide for? What? You can't just go to the stockroom and say, give me some silver ions. You've got to get the negative part with it too. Silver oxide is commonly used. Silver nitrate is commonly used. Because those are more soluble. Your silver halides, not that soluble. You learned in Gen Chem. Ammonium hydroxide helps solubilize the silver. Okay? So don't get thrown off by these reagents. Ultimately, it's a silver. And I think that's the only place you ever see silver in organic 1 or 2 is oxidation of aldehydes. And the tolerance test. Of course, the big 3 will also oxidize the aldehyde. Where else have we seen synthesis of carboxylic acid? Oxidative cleavage of alkenes. with KMNO4. KMNO4 heat, what will it do to the alkene? Oxidatively cleave. We first get, that becomes carbonyl, that becomes carbonyl. But since there's an H on this carbon and that carbon, you got two aldehydes. And what happens to aldehydes with KMNO4? They get oxidized. What reagent would you use if you wanted to stop at the aldehydes? Ozonolysis. Yes. We can oxidize a cyclic ketone, cleave this, that becomes carbonyl ketone. This down here is going to become carboxylic acid. If you used ozonolysis, that would remain the aldehyde. So all this is really review, right? We've seen how to make carboxylic acids before, but now we sort of can focus on, okay, the carboxylic acid part. Synthesis of those. Let's look at the other sheet. Before we move on to the other one and start looking at the mechanism, let's look at some new ways to make carboxylic acids. So we just did A, we just reviewed previous methods. New ways. Reaction of a Grignard reagent with CO2. Very nice reaction. Take this, treat it with magnesium, you get oxidative addition in the Grignard. We know this is, it reacts as if it's the carbanion. CO2 would have this Lewis structure. And because of the individual dipoles, the carbon is partial plus. Partial minus, partial minus. And this carbon is thus electrophilic. It's electron poor. High electron density is going to be attracted to that carbon. These electrons add to the carbon. And either way you want to go, you push electrons over to the oxygen, which would like to have them anyway. This is, we've probably done this before, but this is a nucleophilic addition to what looks like a carbonyl. It's a polarized pi bond. Nucleophiles will add to the carbon, electrons over to the oxygen. What does this arrow movement give? That is now bonded to the carbon of CO2. One double bond remains. The other becomes what? Minus. And we just made that bond right there, yeah? Well, that's your carboxylate. I mean, that's this here. I already had it drawn. That's going to be minus until you add a workup step. You add workup, put the proton on. H plus workup. It'd be a strong acid, like HCl. Something that will protonate that carboxylate. Very nice reaction. CO2 is a gas, but very often you use like dry ice. You make your Grignard and you just throw in dry ice. You don't usually even measure the dry ice, you just throw in excess. Because the excess, after it warms up, will just evaporate. Great way to make carboxylic acid. How does that look? Nucleophilic addition of a Grignard. Really, I mean, lots of nucleophiles will add to CO2. Okay, another way is to use cyanide as a carboxyl synthon. This is the carboxyl group. Synthon is sort of a fancy term for precursor. Okay, it's a carboxyl precursor. But it's kind of a synthesis precursor. It's really two separate steps. Sodium cyanide, triple bond, lone pair. Good old-fashioned SN2, we get the cyanide on the carbon instead of the bromine. But the cyano group can be hydrolyzed to a carboxylic acid. 1, 2, 3, 4. 4 carbons. 1, 2, 3, 4. 4 carbons. This carbon becomes carboxyl group. It is a carboxyl synthon, or precursor. Hydrolysis. We'll actually cover this mechanism a little bit later. I'm not going to do it now. It can either be done with aqueous acid. Hydrolysis. What does hydrolysis mean?
Split by water.
Split by water. It's a reaction with water. And you break apart the molecule. We're going to split this out with water, and we're going to, the nitrogen is going to be eliminated as ammonia or ammonium, depending on the conditions. And if you do it in the pool, it's going to be wet. Do it in the desert, it's going to be dry. You can either do it with water and acid, or water and base. So hydroxide, usually you have to have water. Okay. If you do it with base, you got to have an H+ workup, because if you make this under basic conditions, it will be in the basic form. Okay. We'll look at this mechanism later. When we focus on nitriles. This is 2 ways. Which way is better if you had a choice? Well, show both ways. Show how you would make this carboxylic acid using each way. So show 2 different ways. Now, if you notice, both of these ways, I started with an alkyl halide, essentially. Alkyl halide, you either make Grignard from the alkyl halide, or you do the cyanide SN2 starting with the alkyl halide. So, alkyl halide, you would hopefully see maybe something like this. And then we could react this with magnesium, and then come in with CO2, and then H+ workup, and that should get that over there. Because once the magnesium inserts, we get Grignard. It essentially then becomes this carbanion, magnesium Br, I'm sure that 2+, that minus, but then this attacks CO2, and that's how you get your carboxyl group on there, and you get this bond. You need to sit down and just make sure you see how things are being put together. But this method's going to work. If we do the cyanide method, what do we start with and what do we react it with?
You start with the same thing.
Or the same thing, you react this with sodium cyanide.
You have like a tertiary reaction.
Get that, and then we hydrolyze it. Does that look good?
Yeah.
No. Is this going to work, this SN2? No, you don't do SN2 on tertiary halide. So that's got a problem there. So in that particular case, the Grignard would be best, and the cyanide synthon approach is not going to be good. It's probably going to eliminate. Cyanide will probably act as a base and do an E2 elimination. that make sense? Okay, reactions of carboxylic acids. I think we should move to the other page before we start that and look at general mechanism. Chemistry of acid derivatives. It's pretty much going to be one predominant mechanism for acid derivatives. Just one. And it's called NAS. But it's not nucleophilic aromatic substitution. It's nucleophilic acyl substitution. Acyl typically refers to a carbonyl, although it usually refers to a methyl carbonyl, so it's a little bit not as general as you might think it is. Nucleophilic acyl substitution. What's going on here? We're going to have an acyl group, okay, with some type of X. If the X is an OH, it's a carboxylic acid. If it's an NH2, it's a amide or amide, okay, etc. If it's a chlorine, it's a acyl chloride or acid chloride, okay? We can react this with a nucleophile, and we can substitute the X group with a nucleophile. And we will still have a carbonyl. And when we get to aldehyde ketone chemistry, we're not always going to have a carbonyl at the end. Now, this is a substitution. Everybody agree? Yes. It's not SN1 or SN2. You don't do either one of these mechanisms on the sp2 carbon. The leaving group's on sp2 carbon. Okay? Instead, it's an addition elimination mechanism. And we've actually already saw this during week 1, back in January, when we did like the acyl chloride type stuff. Okay, you got a nucleophile. The carbonyl is polarized because the dipole has partial plus, partial minus. Just like CO2 we showed. So this carbon's electrophilic. The degree of electrophilicity will vary depending on X. We will talk about that a little bit later. But typically it's electrophilic. Nucleophiles will attack. Because nucleophile is typically negative or some type of electron density. If we attack here, which bond are we going to break? Sigma bond to the leaving group or pi bond to oxygen?
Pi bond to oxygen.
Pi bond to oxygen. Some of this we've already said before. So nucleophile adds, electrons up. Nucleophile added, electrons up. We get to this. This is called a tetrahedral intermediate. It's analogous to like a sigma complex, so we just take a sigma bond. But here it's typically called tetrahedral intermediate because there it's trigonoplanar. Now your carbon is tetrahedral. sp3. What do you want to call that step? Addition. More precisely, nucleophilic addition to a carbonyl. That's typically your rate determining step for this type of chemistry. At this point, the electrons can come back down, and now we can kick off anything. R is typically plain carbon, or H, that's not going to leave. Nucleophile could leave, but if it left, you would go this way. Or X could leave. Now you may have to decide which is a better leaving group, X or the original nucleophile. Assuming we're going to get nucleophile to remain, that implies that X has to leave. So electrons down, kick off leaving group. That would be called elimination, that would be typically fast. Because you're going from, if we look down here, reaction coordinate diagram for this, how many intermediates in this overall mechanism? One, tetrahedral intermediate. It's charged. It's going to be higher in energy than starting. That's your rate determining step. Going back down to the neutral product, I am showing it being more stable. That I reckon it usually is. It's not a major thing here. This is more the major thing. Going back down to neutral is going to be fast, and thus the transition state leading to it is going to be pretty low. Okay, that should make sense. We've seen this. So, but rather a what? Addition, elimination. Isn't that what we did? Addition, elimination. It's a two-step substitution that's neither SN1 or SN2. It's actually a lot like NAS from aromatic. Remember when we did NAS, what charge occurred in the ring as an intermediate? Negative. And remember when we did it, I said it doesn't happen. You have to have what to get the mechanism of NAS to happen? Strong electron, strong group, ortho-para. Then we did resonance structures, and we said the reason that helps is because the negative ends up being put on what type of atom? Heteroatom. Like an oxygen. Anytime you do a nucleophilic addition to a pi bond, it typically can only occur if you can put the resulting anion on an electronegative atom. Can this occur? Where do we put the anion in? On an electronegative atom. Okay? Now there's no resonance of it like in NAS. But still, that will occur. Now, anytime, we'll say this before. We've said it before, I'll say it numerous times again. Anytime you can make a pi bond with a lone pair, I'll usually leave out the lone pair part. Anytime you can make a pi bond and kick off a leaving group, that's usually fast. And indeed, I show you this fast. Okay. Which step does the leaving group leave in? Fast step. That also makes it different from SN1, SN2, because in those SN1, SN2, leaving group leaves in the rate determining step. Since leaving group leaves in the fast step, just like NAS from aromatic chemistry, leaving group ability is not the same as SN1, SN2. It's actually not as important. And lots of things can be leaving groups. Nitrogens and oxygens commonly leave without being protonated. Maybe see a carbon leave if it's stabilized somehow. Actually, guess which halogen is your best leaving group? Fluorine. Actually, fluorine is the best leaving group. Why? Because it makes the addition faster, because of the fluorine making the carbon more electropositive. It's not the leaving group ability that we're used to from organic 1. Okay, that's pretty much what I just said here. Iodine is the best in SN1, SN2. We'll even see carbon leave. At some point, let's test 4. This is a carbon that's going to leave. It'll be stabilized. It's stabilized carbanion. Okay. Additional elimination. I reckon I'll go ahead and do the reactivity discussion. Here are several acid derivatives. These are your carbonyl containing acid derivatives. The nitrile is not included here. Okay. Obviously, a nitrile doesn't contain a carbonyl. Reactivity. This is more acid chloride. What is this called? That's an anhydride. And those of you that have used acetic anhydride in lab, if these are methyls as shown, that's acetic anhydride. Okay? What is this? Ester? And then an amide. Acid chlorides are your most reactive. That means they're the most electrophilic. Then anhydride. Going down the line. These two are so reactive that they'll actually react with pure water. Because of that, you don't find them in nature, because in nature, guess what's out there? Water. Water, and so they can't survive. Okay? These are not going to be drugs, because if they were, you give them in the body and they're going to be hydrolyzed by water. Water will attack them. Also, they're toxic because things that are electrophilic tend to be toxic because your biomolecules will attack them. Okay. Now, esters will not react with pure water. You find esters in fruits where there's water. Esters are fragrant. Scratch and sniff, that's usually an ester. And then amides. Amides tend to be hard to hydrolyze. They're least reactive. So why? It all has to do with the partial plus. There versus here. There's more partial plus here. Now they all have this. We'll talk about two. When there's two, basically, you do chemistry at one, the other portion is a leaving group. They all have that, so that's not your answer. The difference is the X group. And so what does a chlorine do when it can do both?
Withdrawals.
It's a net withdrawer. So it's pulling. So that makes the partial plus even greater. We'll kind of skip here. There'll be some more discussion. But down here, what does the nitrogen do net? Yeah, the nitrogen donates. So that's going to kind of quench the partial plus as much. There's not as much there. It's like this is a a poor college student, and then it's got it owes a lot of money, but then it's got a friend that needs money too, taking their money. Might be happen to be a girl. But over here, this friend has a rich buddy that's okay. So this guy's not feeling the pain as much. Donating. Okay. So that's pretty much what I said here. Why is the anhydride not as electrophilic as the acid chloride?
Electrons.
Now, actually, I want to... Here. Why is this more reactive than this? They're both oxygens. So more resonance is kind of a vague. A little bit vague.
I thought it was always the answer.
Always the answer? More resonance? Even when there's not any resonance? There's a pi bond nearby. It's got to be resonance. Not always. Depends on orbital overlap. Is this guy going to be able to donate? No, because this guy, you might say it donates, but guess what? It also donates this way. 2 times. Okay? So if it donates that way, it actually takes on positive in a resonance structure, and now it's withdrawing. But if you look at just OR, these electrons are not being pulled the other way like that, and so this can donate more. So that's why the ester is less reactive than the anhydride. Even though they're both oxygens, this oxygen is being pulled the other way some. Now with amides, why is the amide less reactive than the ester? They're both, one's oxygen, one's nitrogen. They're both kind of like group 1 from our ES discussion, the lone pair that can donate. Which donates more though? Why would nitrogen donate more? Because it's less electronegative. It's less greedy. Oxygen will donate, and you can show this resonance structure. By the way, I'm leaving one out. Resonance structure I'm leaving out is if you just move these up, we could just see Okay? If you just do resonance structure, you see the positive. And from there, you can kind of move these in, and that would give this. And this shows how the X group can sort of quench the positive charge. All right? But see, this oxygen, while it will donate, and it will take on a positive, we've done that many times, if you compare it to the nitrogen, it's not as willing to as the nitrogen. Because oxygen is like, hold on now, I'll donate, but I don't like this too much. Nitrogen is like, here, take them up, compared to that. Nitrogen is less electronegative. Nitrogen donates more, even though they're both sort of group 1 of the EAS discussion. So AMA has that strong nitrogen donating to the carbonyl, makes it less electrophilic. Now, resonance. This is DMF, dimethylformamide. We show the donation by resonance, we can show this resonance structure. Key thing with amides is, because of this strong donation, the oxygen has lots of minus charge in the hybrid. So there's lots of minus there, there's actually partial plus there. So if you blend these two together, you end up with this blend. Now what do you think about this resonance stuff? Have I ever given you proof of resonance? Actually, yes, but... How about some NMR proof? Let me ask you a question. Look at these methyls. Are these equivalent or not? Now look, if that was a carbon over there, a carbon with 2 methyls, are those methyls equivalent?
Yes.
Yes. There's a CH here. You make that a nitrogen, are they equivalent?
Yes.
Yeah. In theory. But if this contributes a lot, we start putting double bond character between the nitrogen and the carbon. And if the double bond is really there a good bit, what's that going to do to this free rotation? It's going to keep it from rotating. If it's not rotating, one methyl is cis to the oxygen and one is trans. So does it have free rotation? Or does this structure contribute a lot and the rotation sort of fixed or inhibited? Well, look at the NMR on the next page of DMF. Here's the H, it's sort of like an aldehyde. Way down field at 9 to 10. This is water. Every NMR's got water in it. Every real NMR does. There's water in the atmosphere. And you typically don't do a background when you do NMR like you do IR. What do we have here? 2 methyls. So are they equivalent? Why are they not equivalent? Because there's really significant double bond in here limiting the rotation. To me, that's some evidence of this idea of resonance hybrid. What do you think of the evidence? Okay. Let's look at interconversion of acid derivatives. You only convert to a less reactive derivative directly. You can indirectly make anything you want with multiple steps. For example, acid chloride can be converted to an anhydride, an ester, or an amide. Because these 3 are all less reactive. An ester can only be converted to what? Amide. An amide, because it's the only one that's less reactive. You're not going to directly convert an ester to an acid chloride. You're not going to convert an amide to an acid chloride.
So an anhydride can go to an ester or...
Yes, an anhydride can go to an ester or an amide. Yes. And if you look on the front page, I have these listed in terms of reactivity and height. Acid chloride is higher, anhydride is lower, ester is even lower, and then the amide is the lowest. I haven't included nitrile in the reactivity scale. So you see that the acid chloride can be converted to any of these. So that's organized that way. Now why can you not do this reaction right here? React this with Cl- to make the acid chloride. Well, consider the reactivity scale. This is not that reactive. And chlorine, even though it's minus, is not a great nucleophile. Yes, we might have called it strong in organic 1, but it's the weakest of the strong. So you just don't have good reactivity there. Not a great electrophile, not a great nucleophile. Also, the leaving group ability. If you look at the X groups that are here, boom, 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 these can all leave. But you still want to consider which one is best. And halogen is still going to be your best leaving group. Nucleophilic ability of your leaving groups. The nitrogen anion is going to be your strongest nucleophile. And that's your weakest. So what I just set up here. So let's show a scenario and explain why it just doesn't happen. This going to there. Okay, we're asking a poor nucleophile to attack this poorly electrophilic carbonyl. It's just not good. But even if it did, we'd get to this point. And when this comes back down to reform carbonyl, which is a better leaving group, nitrogen or chlorine? Chlorine. Chlorine. So it just comes back. On the other hand, if you went the other way and had an acid chloride reacting it with ammonia, ammonia is a good nucleophile, even though it's neutral. Because nitrogen's a lousy parent. Let these electrons get out there. Very reactive. So you got two very reactive substrates. Nucleophilic addition. At this point, I have lost an H here. So let's draw another arrow. Okay, you can't just lose an H. So there's multiple steps here. We'll talk about this. But at this point, when you come down, which is going to get kicked off, Cl or N?
Cl.
Okay. So the chemistry is set up to give you a conversion. All right. We'll have to talk about that. Yes, we'll have to deal with it. The carbonyl chemistry, I think I've said before, we'll always have to deal with the proton. Proton.
Dr. Steve, the fact that the Knox equation, the one that didn't work with the Cl minus, protonating the NH2 then would change that whole scenario.
At the very beginning?
Yes.
I mean, possibly, but it's still not going to work because a positive nitrogen is still not as good enough leaving. It's still not better leaving group than a Cl.
Okay.
But it's close. How do I know that? I'm just coming to that conclusion because I know the reaction doesn't work. Okay, with a little bit of time we have left, let's look at reactions with carboxylic acids. We've already, this is sort of similar. Test 1, we reacted alcohol with thionyl chloride, and we got an alkyl chloride. The OH was replaced with the chlorine. We're going to replace it with the chlorine here with thionyl chloride, but we're going to use Acl substitution chemistry. Thionyl chloride. Okay. Here's where most books lie to you, at least one of the examples. They lie to you a lot of places. Which oxygen, nucleophile will attack this sulfur, very electrophilic, all these greedy atoms bonded to it. Which oxygen is more nucleophilic?
Pi bond.
If you do resonance, you would use these electrons, and you would do resonance. That's resonance involving the lone pair that's in the p orbital. These lone pairs aren't in p orbitals up here. There's your resonance. So in the hybrid, what type of charge is on this oxygen?
Negative.
What type of charge is on this oxygen? Okay, which oxygen is nucleophilic? The negative one. Okay? Now books will probably show you using this oxygen. I'm going to use this one. These electrons attack sulfur. When you attack sulfur, what are you going to do here?
Great pi bond.
I bond up. It's almost like a carbonyl. That's going to give boom, boom, boom. That becomes minus when the pi bond goes up. Chlorine, chlorine. OH, positive. Lone pair, lone pair. Now let me draw one more structure and we'll end there. Let's do resonance here. Let's forget about that for a minute. Let's do resonance. These electrons in, these electrons out. That's resonance structure. Basically, you're to a similar point as if that oxygen attacked. From here, I want you to finish this mechanism up. Okay? You got to keep in mind, guys, I expect you to use things and knowledge we've learned back in test 1, like when we did oscillate. Okay? All right, you should be able to do this. Standard electron movement. See how you do. See some of you this afternoon. Remember your data table you can turn in next week for lab. Have a good day, guys.